My name is Panagiotis Kassanos, and I will be presenting our work on an interdigital strain sensor fabricated through laser carbonization of polyimide and subsequent PDMS transfer. I will talk about applications of soft strain sensors that are of interest to us, and also briefly talk about additive fabrication techniques and laser carbonization. I will then move on talking for the sensor fabrication process and sensor characterization, and I will then conclude my presentation and briefly talk about our current work. There are a wide range of applications for strain sensing. Within the context of our work, we are primarily interested in measuring stress applied on tissues to avoid injury. Within this field of space applications, of interest is the prolonged use of spacesuits and the resulting shoulder and finger injury. Within the context of surgical robotics, there is an interest of monitoring forces applied to sensitive tissues. Another application of interest is the use of strain sensing for monitoring robot motion and the use of this information to allow closed-loop motion feedback control. There is a number of different ways to monitor strain. There are resistive, capacitive, inductive, and piezoelectric strain sensors, as well as strain-sensitive transistors. Of course, there are also optical sensors, such as fiber Bragg gratings. Additive fabrication techniques have attracted significant interest in recent years. This is because they have the potential of allowing clean room-free fabrication using simpler fabrication protocols and equipment and facilities that are of lower costs, while also requiring lower quantities of materials, as they are additive rather than subtractive processes. There are a number of different approaches to achieve additive printing. These include stencil, screen, inkjet, gravure, stamp, and flexographic printing, as well as extrusion-based 3D printing and laser-induced forward transfer. What is common between all of these techniques is that they require specialized inks. Laser carbonization is another approach that has attracted interests. The use of a CO2 laser engraving system of polymer films allows the realization of electrically conductive carbonized features on a polymer substrate. Only specific polymers can be used, those with aromatic and amide repeating units, such as polyimide and polyetherimide. It is a photothermal process that breaks down the chemical bonds within the material, leading to the reduction in the contact of the nitrogen and oxygen that are released as gases, leading to a porous structure within the carbonized features. Higher laser powers lead to higher electrical conductivity, but also to a more fragile carbon pattern. One advantage is that there is no need for an ink. Nevertheless, as mentioned earlier, there is a limitation of the types of substrates that can be used for the patterning, and the conductive material that is achieved is limited to carbon. Nevertheless, with additional post-processing steps, additional functionalities can be introduced. Without specialized geometrical patterning, the device realized with this approach is not stretchable. However, it is flexible. Stretchability can be achieved by transferring the carbonized features onto PDMS or other elastomers. In this way, essentially a carbon-based conductive elastomeric composite is achieved that is embedded directly onto an insulating substrate. The fabrication process is simple. In our case, we have used a polyimide film that we have cleaned with IPA and then placed within the CO2 laser system. We have used the high-power density focusing optics module of the machine and a power of 4.2% and a speed of 5%. In this way, we pattern our geometry onto the polyimide substrate. We then use a spray coater to blow air on the device and remove any carbon debris to reduce the possibility of short circuits. We then dip the device in heptane for a minute, and then we wash a few times with heptane with a PET to remove any remaining carbon debris. We then take the device on a Petri dish and we pour on top of it a diluted 10:1 PDMS with 7% heptane. With the gas, we place in a vacuum oven and with the gas again and bake for 2 hours at 70 degrees. Once the PDMS has matured, the device is removed from the oven and the PDMS polyimide stack is separated, leading to the transfer of the carbonized features onto PDMS. The picture on the right shows the realized interdigital strain sensor. We have achieved a finger width of 133 micrometers a finger gap of 170 micrometers, an interconnect and finger gap of 200 micrometers, an interconnect width of 583 microns, and in this case, we have used a PDMS substrate thickness of 2 millimeters. Nevertheless, using this approach, we have achieved similar devices with PDMS thicknesses down to a few hundred microns. First, we characterized the device under no applied stress by placing it on a flat substrate. The impedance was measured, and the impedance spectra were then used to fit the values of the equivalent circuits shown below. R0 models the resistance of the conductive tracks, and the inductor models the inductance of these tracks. C is the capacitance between fingers and through the substrate, and R models the resistance through of the substrate, hence the Hertz value. This picture shows the experimental setup used for characterizing the sensor. It is composed of two stages, one of which is controlled by a motor. On top of this, we have a set of clamps that hold the substrate, the device, one of which is connected to a force sensor. While the distance between the two stages is changed, the force is measured, and through a caliper also the elongation of the device. Mechanical deformations will change the insulating substrate thickness, and they will also change the distance between the interdigitated electrodes. Both of these will lead to changes in capacitance. At the same time, the resistance of the conductive tracks will also change, as carbon-based elastomeric composites are highly piezoresistive. These changes are measured by measuring the impedance of the device at multiple frequencies. Within the applied forces we examined, of 1 to 5 newtons, we found that the device elongation varies linearly with force. At low frequencies, obviously the capacitance of the device dominates. For less than 2 kilohertz, we see that the phase is unaffected and constant to about minus 90 degrees. As the frequency is increased, however, the resistive part of the device plays an increasing role. For frequencies greater than 10 kilohertz, the phase starts to react to strain. The reactance is decreased, and changes in the real part are more evident. For 2 kilohertz and above, also, the measurements are less noisy, and this is due to a reduced impedance of the device from 10 to the 8th at 500 Hz to 10 to the 6th at 50 kilohertz. We have also found that the impedance magnitude percentage change varies linearly with applied forces, and this has been found to be about 1% per Newton, irrespective of the frequency used for the measurements. To conclude, laser carbonization of polyimide films is a promising approach for the realization of flexible stretchable sensors. Transfer to PDMS allows device stretchability. The interdigital structures realized demonstrated a strength sensitivity when subject to mechanical deformations of about 1% per Newton. Currently, we are examining the application of these sensors and fabrication technology to allow pressure and strain sensing in surgical robots. And we are also examining the realization of additional sensing functionalities. I would like to thank our colleagues from the Imperial College Physics Workshop for access to the CO2 laser, and our former colleagues Jingdong Yu and Rachel Tobin for help with the tensile stress setup and the 3D printed fixtures. I would like also to acknowledge financial support from the PSRC through the Microrobotics for Surgery and Future AI and Robotics Hub for Space program grants. Thank you for your attention.